Um, Hello, everyone from snowy Boston. Thank you very much for the invitation to speak. I must apologize in advance. There is not going to be any gauge fields or any gravity in my talk, but there are going to be some boundaries. So maybe that's the connection to the previous talk. So I'd like to actually discuss a very old problem, but one where it seems that certain things have been overlooked. So this is the problem of boundary criticality in the ON model. So let me remind you about boundary criticality. So what does this mean? Well, we take a theory in the bulk which is at a critical point, perhaps described by a conformal field theory, and we want to study its behavior near the boundary. For instance, we might want to calculate correlation functions of operators on the boundary, and maybe some correlation functions involving both boundary and bulk operators. And there are two observations that we must make immediately. First observation is that the physics on the boundary is generally different from that in the bulk. For instance, the scaling dimensions of boundary operators, denoted by delta hat here, will be in general different from bulk scaling dimensions. A second observation is that given a bulk critical point, a bulk fixed point, the boundary universality class might not be unique. There can be more than one boundary to a single fixed point. Think of them as kind of different boundary conditions. And to tune between those boundary fixed points, you just change the and we will see some examples shortly. Now, this is a very old subject, going back to classical statistical mechanics in the 70s and 80s. But there has been some renewed interest in it recently. I think coming in particular from two directions. First direction is from we now have a better understanding of conformal field theory, in part due to conformal bootstrap. So that's one direction. A second direction comes from the physics of symmetry-protected topological phases. So these phases are, of course, gapped in the bulk and have some protected boundary states. And the question that has... so for a very long time, it was thought that the bulk gap is actually crucial for the protection of the boundary. However, it has been realized that actually, in some cases, even when the bulk gap closes, something of the non-trivial boundary state survives. I think this paper by Tarun Grover and Ashwin Vishwanath was one of the first to discuss this phenomenon, and yeah, there have been a number of examples worked out since then. So if I have time at the end of my talk, I will return to a particular instance of this problem of so-called gapless symmetry-protected topological phases. But actually, most of my talk is going to be just about classical statistical mechanics, and in fact about the simplest model of classical statistical mechanics, the ON model. And I'll try to convince you that even in this model, something was overlooked in regards to boundary criticality. So let me remind you about this classical ON model. Okay, so we take a d-dimensional lattice and we place classical spins Si on each side of this lattice. We take them to have n components, and the length of each spin is 1. So just classical n-component vector. And we couple them with nearest neighbor coupling Kij, taken to be ferromagnetic here. So this is the classical Hamiltonian. And well, what is the phase diagram of the system? The bulk phase diagram is as we tune the temperature, we have a phase transition from a high temperature disordered phase to a low temperature bulk ordered phase. What about the physics on the boundary? Well, the physics on the boundary depends on the boundary coupling of the spins. So let me consider a very particular model where the coupling of the spins in the bulk is given by K, and on the boundary it's given by K1. And let me look at the phase diagram in this K1 in this plane of temperature and the ratio of the surface coupling to bulk coupling. So we already discussed the bulk phase diagram and this bulk phase transition at T equal to Tc. And of course, this bulk critical temperature is unaffected by the boundary coupling K1. But what about the various phases of the boundary? Well, it turns out that if, first of all, if the bulk dimension d is greater than 3, little d will always stand for the bulk dimension here. If the bulk dimension is greater than 3, then it turns out that if surface coupling is not too large compared to the bulk coupling, then the surface and the bulk order at the same temperature. And this is known as the ordinary boundary universality class. On the other hand, if you make K1 large enough, then it's possible for the surface to order at a temperature which is higher than the bulk critical temperature. So then as you lower the temperature, you first go into a phase where the surface is ordered and the bulk is disordered. And this is just a surface transition in the d-1 dimensional ON universality class. And then, as you keep lowering the temperature, when you hit the bulk Tc, the bulk orders in the presence of an already ordered boundary. This is known as the extraordinary boundary universality class. And then there is a multi-critical point here known as the special. So this is yet another boundary fixed point. So this is the phase diagram in dimension d when the bulk dimension d is greater than 3. Well accepted. Now there is one interesting point, which is that up till now I've discussed the phase diagram in the absence of any symmetry breaking fields. You can also discuss the phase diagram when you turn on a field on the boundary which breaks the ON symmetry. Right? Just turn on a magnetic field only on the boundary. So it's believed that in this case there is just one universality class, one boundary universality class, known as normal boundary universality class. And an interesting fact is that when the bulk dimension d is greater than 3, it's believed that this extraordinary universality class is actually the same as the normal. It's easiest to understand. The essence is that it doesn't matter whether you break the symmetry, the ON symmetry on the boundary explicitly or spontaneously. Once you have a finite expectation value of spin on the boundary, you have the same transition. And it's easiest to understand in the context of Ising spins, where the order is kind of rigid, but it's also believed to be true for ON spins with general n, as long as d is greater than 3. Essentially, the fluctuations of the Goldstone modes of the surface ordered phase decouple at the extraordinary transition for d greater than 3. All right. So this is what's known about the phase diagram for d greater than 3. What about d equal to 3? This will be the subject of my talk. Well, if you have Ising spins, then the story is exactly the same in d equal to 3. Same phase diagram, same boundary universality classes. What about xy spins, n equal to 2? So here the physics becomes more interesting already. We know that for xy spins, you cannot have in 2 dimensions a phase with true long-range order. You only have quasi-long-range order. So this corner of the phase diagram here now has quasi-long-range surface order and no bulk order. And the green phase transition here is just a 2D costless-styleless transition. But what about the extraordinary transition in this case? What about the phase transition from this quasi-long-range ordered surface phase with the onset of bulk order? Surprisingly, this question has not been discussed very much in the literature. In fact, the only meaningful discussion I could find was in this paper by Deng, Blot, and Nightingale from 2005, which is a classical Monte Carlo paper on this problem. They just studied the phase diagram with a classical Monte Carlo, and the way they interpret their data, at least one of the interpretations they put forward, is that even though in the above the bulk TC you cannot have true long-range order, perhaps right at the bulk TC you have a true long-range order on the boundary. That is, the boundary order parameter has a jump across the bulk TC. So this seems to be roughly consistent with their data. But this seems also like a very strange scenario, but it's actually hard to rule out off the top of your head, because while the Mermin-Wagner theorem applies here above the bulk TC, at the bulk TC, the bulk is critical, so it can induce some power law interactions of the boundary spins, and if those power law interactions are of sufficiently long-range nature, Mermin-Wagner theorem does not apply anymore. So, just from first principles, it's difficult to rule out this scenario. Nevertheless, as I'll convince you, this is actually not what's going on at this extraordinary transition. There is no long-range order on the boundary at the extraordinary transition. Rather, what happens at the extraordinary transition is that the correlation function of boundary spins decays very slowly, like a power of the logarithm of separation. So it's a kind of quite unusual scaling, but that's what we find, and this exponent q is universal. Another finding is that if you approach this extraordinary line from above, in the quasi-long-range ordered phase, of course, the Lattinger exponent kappa, characterizing the power law decay of the spin correlation function, can vary, and I find that it actually varies like this. It diverges logarithmically as you approach the bulk TC. Okay, so I'll substantiate this with some RG calculations, but and further, I term this kind of transition the extraordinary log universality class to distinguish it from the more conventional extraordinary transition in D greater than 3. All right, so this is as far as xy spins are concerned. What about when n is greater than 2? What about say Heisenberg spins or 3 spins and higher n? Well, in this case, of course, when we are above the bulk TC here, the surface always has a finite correlation length. They cannot be classically, they cannot be either quasi-long range or true long range order for n greater than 2 in 2 spatial dimensions. So then, just the topology of the phase diagram does not mandate a separate ordinary and extraordinary universality classes as it did here. It's possible that for all values of the surface coupling, you have the same ordinary boundary universality class. And this, I think, is what people had at the back of their minds in the literature. However, it's also not prohibited that you have two distinct boundary universality classes as a function of the surface coupling, even though they connect to the same surface phases above the bulk Tc and also below the bulk Tc. So which one of these two phase diagrams is realized? And as I'll try to convince you, the answer actually depends on n. When n is large but finite, we have the phase diagram on the left here with only the ordinary universality class. On the other hand, when n is just slightly above 2, we have this phase diagram here on the right, and again the extraordinary universality class is of the extraordinary log type with a correlation function on the boundary decaying as a power of logarithm of separation, and the only new thing compared to the n equal 2 case is that this q starts to depend on n. Now here I'm treating n formally as a continuous parameter. That's why I take it just slightly above 2, but yeah, so the most interesting question, of course, is where do integer values of n lie, and yeah, I'll discuss this as we go on. But this is what the theory can predict reliably. All right. So let me sketch a renormalization group treatment that leads to these conclusions. So I want to be in the regime of the phase diagram when the surface coupling K1 is large, so there is a strong tendency to local order on the boundary. So let me call the boundary order parameter n of x, and describe it by a nonlinear sigma model like this. Now if we only had the boundary and no bulk, this would be just a two-dimensional nonlinear sigma model, and we know the fate of this model. Polyakov has taught us, so we can do a renormalization group on this model, and we find that this coupling G runs in the following way. That is, G runs away, even if we start with the initially small g, G runs away to infinity, and this signals the fact that we always have a finite correlation length for the ON model in two spatial dimensions. Now the question, the key question is, how is this RG flow modified when this nonlinear sigma model lives on the surface of an already critical bulk? Well, this is really the crux, but I'll just tell you the answer. Turns out that the coupling to the bulk modifies this RG flow, and in particular just modifies the prefactor of this G squared term. Let me call the prefactor minus alpha. So here is the surface contribution, but there is an extra contribution coming from the bulk, and it's parameterized here in terms of a universal constant S, which in turn is related to a ratio of certain universal amplitudes at the normal fixed point. Remember, the normal fixed point is the one where you have an explicit symmetry breaking field on the boundary. But for the rest of my talk, it will not be very important, what this S is. So just take this formula as given. So what is the fate then of the boundary? Well, the fate depends on the sign of this alpha. If alpha is positive, then g runs logarithmically to 0, and this is precisely the extraordinary log fixed point that I've advertised. If you integrate this flow together with the anomalous dimension for the boundary or the parameter, you find that the boundary spin-spin correlation function indeed decays as a power of logarithm, with the exponent q being related to this coefficient alpha. All right. On the other hand, if alpha is negative, then g equals 0 fixed point is unstable. G runs away from 0, and we will discuss where this flow is towards shortly. So, is alpha positive or negative? That's the question. And well, for general value of n, we cannot say with certainty, but there are certain limits that we understand. So first of all, when n is equal to 2, there is no boundary contribution to this alpha. There is only the bulk contribution. And the bulk contribution is manifestly positive. So when n is equal to 2, alpha is positive. On the other hand, when n goes to infinity, we can use large n expansion to calculate this s explicitly. And here is the answer that one gets, and one finds that for large n, alpha is in fact negative. So that means that alpha must actually change sign as n increases from 2 to infinity. And I will make a minimalistic assumption that it changes sign just once at some n equal to n.
May I ask a question?
Yes, of course.
So at this point, do you assume that the bulk is a critical point?
Yes. Yes.
Or it's an ordered phase?
No, the bulk. We are sitting right here at the bulk TC.
I see. Okay, thank you.
Mm-hmm. Right. So very good. So alpha changes sign at some n equal to n, some critical value nc. For n smaller than nc, we have a stable extraordinary log phase. What is the value of nc? I think the honest answer is we don't know. If you just take this large n calculation, you know, I've been able to calculate the subleading term here and extrapolate it to moderate values of n, one gets nc close to 4. Take this with a grain of salt for now. All right. So what is actually the evolution of the system across n equal to nc? Well, for n close to nc, this coefficient alpha is small, right? So we can just linearize it like this, near n equal to nc. And the physics will really be controlled by the subleading term, by the next order term in the beta function. So there are two possibilities. Either the coefficient of this term is positive or it is negative. Let's begin with the first possibility. If the coefficient is positive, what happens? Well, as n approaches nc from below, you find that this beta function has an infrared unstable fixed point at a perturbatively accessible value of the coupling g, and we associate this fixed point with a special transition. We know that for n equal to 2, we have this special transition between the extraordinary phase and the ordinary universality class. And then, well, we just expect that as n approaches nc, in this scenario, this special fixed point approaches g equal to 0. And then finally, when n is equal to nc, the two fixed points, extraordinary and special, collide and disappear, such that for n greater than nc, we have just the ordinary fixed point left. And again, for n close to nc, all the properties of this special fixed point can be calculated, such as scaling dimensions. All right. So this is the first scenario. Second scenario is b is less than 0. So this is a little bit more involved. Here, as n becomes slightly larger than nc, the extraordinary fixed point, the stable, infrared stable extraordinary fixed point, actually moves away from g equal to 0 to some small finite value of g, and at this, we call this extraordinary power universality class, because at this extraordinary power fixed point, we have true power law scaling of the boundary correlation functions, not this kind of logarithmic scaling. And then this extraordinary power fixed point eventually must disappear, because we know actually from large n calculations that at n equal infinity there is only the ordinary universality class, so there must be another critical value of n where it collides with the special fixed point. So these are the two scenarios. We don't know what sign B has, so we must take them. We must kind of consider them on an equal footing. So really, the most pressing questions are which scenario is realized and what is the critical value of n and c. And well, at this point, all the analytical considerations. I've exhausted all my analytical arguments, so one must turn to numerics. Actually, Adolfo, how am I doing on time?
You have like 5 minutes or more or less.
Okay.
Maybe a bit more if you need, but you will be eating time of questions.
Okay. Yeah, let me then talk about this numerics. So before my work, actually, there was very little numerics on this problem. So I mean, of course, we already know what the phase diagram looks like for n equal to 2. It's both from analytical and numerical arguments. We know this is the shape of the phase diagram. Numerically, people didn't know what is this extraordinary universality class, or analytically for that matter, but at least the topology of the phase diagram was clear. So the next point is n equal to 3. What is the topology of the phase diagram for n equal to 3? And before my paper came out, there were only 2 studies of this question, and they actually reached different conclusions. The first study here concluded that actually there is just one universality class, the ordinary universality class for n equal to 3, and that simply as you increase the boundary coupling, you have a longer and longer crossover to this ordinary universality class. However, this subsequent paper studied the analog of the Binder ratio, but for the surface order parameter. And what they found was that there was a crossing in this Binder ratio, which is kind of indicative of a surface phase transition, which they associated with the special transition. But they were not able to say, okay, for even larger couplings on the boundary, what is the nature of this extraordinary phase. And there is also one study for n equal to 4, which also seems a similar crossing point in the surface Binder ratio, very quite similar to n equal to 3. All right. So now, after my paper, there's been a couple of developments in classical Monte Carlo. By the way, all of this is classical Monte Carlo. Couple of developments. First is this paper by Francesca Toldin, which studied quite carefully the n equal to 3 case. And again, he found a crossing point in the surface Binder ratio, which he associates to a special transition, and he was able to extract the exponents, various scaling dimensions at this special transition. He also studied the extraordinary regime, the regime of large boundary coupling, and it seems to be consistent with the extraordinary log phenomenology that I have described. For instance, here is the plot of the stiffness. Remember this 1 over g, the coupling constant, is exactly the surface stiffness, and the prediction is that this surface stiffness should grow logarithmically and well, it does seem to grow kind of logarithmically. And here is the 2-point function of spin on the boundary, and you see it decays very slowly. One can try to feed a power of logarithm to it, and from these two observables and some other observables, Francesca concludes that this universal number alpha is something somewhere in this range.
Sorry, how does this alpha related to Q? To the power?
Yes, this is the relation.
Ah, okay, thank you.
Yeah, so I think he extracts this 0.11 from stiffness, and he extracts 0.15 from this 2-point function. Okay, so it seems from these numerics that n equal to 3 lies below nc, and there is an extraordinary phase, an ordinary phase, and a special transition between them. There's also, just 2 days ago, there came out a study of the n equal 2 model, again classical Monte Carlo, in the large surface coupling regime in the extraordinary phase. And again, it seems to be consistent with extraordinary log phenomenology. Here, I think the data is even more clear. Here is the stiffness. Again, it grows logarithmically with a system size. They actually try different boundary couplings. All of them seem to have the same slope. And here is the 2-point function on the boundary. And again, it seems to decay as a power of logarithm, and they actually were able to verify this relation between Q and alpha, and extract alpha roughly 0.27, right? So alpha does depend on the value of n. And remember, we said that alpha should decrease as n is increased, and indeed it seems to decrease. This is n equal to 2, this is n equal to 3. All right. So furthermore, numerics seems to be consistent with this first scenario, where the special fixed point approaches the extraordinary log fixed point as n is increased towards nc, and then collides with it and disappears. Why? Well, remember, in this scenario, the special fixed point becomes perturbatively accessible for n close to nc, and the scaling dimensions of the boundary order parameter and the inverse of the correlation length exponent at the special transition actually becomes small for n close to nc. Let's look at this, at what classical Monte Carlo says about this critical exponents at the special transition. So indeed, as n increases, we see that they decrease. Both of them decrease. This data for n equal to 4 I would take with a grain of salt, but at least I think the values for n equal to 2 and n equal to 3 are probably more reliable. Okay, so this is what we know from classical Monte Carlo at this point, and indeed, things seem to be consistent with this extraordinary log story, both for n equal to 2 and n equal to 3. Now, there has actually been quite a bit of quantum Monte Carlo on this problem. Let me very quickly maybe describe it. So this quantum Monte Carlo is on models of this type. So it's two-dimensional quantum spin models, two spatial dimensions, and it's there's actually different geometries that have been considered. But let me consider this geometry discussed in various papers by Stefan Wessel and Lucas Weber, which is kind of a dimerized rectangular lattice where we have a strong coupling on these red bonds and weak coupling on the black bonds. So this spin model in the bulk has a transition from a trivial paramagnet when these red bonds are very strong to a null phase when red bonds say are equal to black bond strength. And this transition is known to be in the classical O3 three-dimensional universality class, just as the classical transitions that we were discussing a moment ago. What's interesting, what's kind of more recent, is that people started studying boundary criticality in these quantum models, and there are two kinds of boundaries they consider. They consider this non-dangling edge, where the spins are part of the strong red bonds, and the dangling edge, where they're part of the weak black bonds. And they actually found different boundary criticality at these two edges. But again, boundary criticality means that they sit at this bulk transition point and study the boundary. So for the non-dangling edge, they find a scaling dimension for the boundary spin, which is very similar to that at the ordinary fixed point in the classical O3 model. But at the dangling edge, they see a very different scaling dimension. It's roughly 1/4. So this was the puzzle. And this same scaling dimension is actually seen in a number of microscopic models. So the initial thought was that this scaling behavior at the dangling edge is due to the fact that even if you go to the paramagnetic phase here, the dangling edge has spin has spin sitting on it, and in particular, if it's spin 1/2, then it's a spin 1/2 chain, so it's gapless, Heisenberg chain. So then even in the paramagnetic phase, you have gapless edge, so it cannot be the ordinary transition, because ordinary universality class, once you go into the paramagnetic phase, you have a finite correlation length. So people thought that maybe this dangling spin 1/2 dangling Heisenberg chain has something to do with this unusual behavior. But then they found actually similar exponents for spin 1/2 and spin equal to 1. This was really surprising, at least to me. And for spin 1, we know that the spin 1 chain is gapped, so there is no the correlation length on the boundary on the paramagnetic side is fine. So what's going on? Well, let me very quickly tell you the working scenario, at least at the moment, is that this dangling edge is controlled by the special transition in the O3 boundary universality class. Somehow the guess is that these models are accidentally close to the special fixed point, and if you really went to very large system sizes, you would be able to see a crossover either to the ordinary or to the extraordinary behavior. But this hasn't been seen in numerics till now. This puzzle of spin 1/2 and spin 1, why they are similar, I will leave for questions. So let me stop here. Thank you.
Thanks a lot, Max, for the doc. Any questions? There were already a few. Baptiste, and then Alex.
Maybe just a quick question. You talk about the d equal 2 with different n. Do you know anything about the d equal 2 case? Because you talk about d equal 3 and d equal 2 plus 1, but what about classical d equal 2 case?
Yeah, so there we are in the realm of conformal field theory, boundary criticality in two-dimensional conformal field theory, and that's a very well understood subject. There is this work by Cardy, boundary universality classes are kind of in one-to-one correspondence with Yeah, there are these conformal boundary conditions.
Alex?
Suppose we were godlike and could integrate out all bulk degrees of freedom for a fixed surface configuration. Do you have any idea, I mean, if you could dream up a term for an effective surface field theory, probably a non-local term, I mean, that helps the 2D sigma model not to disorder? I mean, there are a few obvious candidates, but I ran a cross-check in the back of my mind. I couldn't think of any.
Well, okay, so I'm not sure this is actually a super productive way to think about this particular problem, but if you wanted to just have a purely 2D model with power law interactions, then if you add like n of x, 1 over x minus y to some power q, 1 over n of x, then it actually will be in general it will in general have an ordered phase when the exponent of the power law is small enough. You can convince yourself. It kind of modifies, right? Instead of the gradient n squared term, you now have kind of a non-analytic term, which is kind of momentum to some power smaller than 2 times n. So if that power is smaller than 2, then you're in good shape. It's stable.
Including for a nonlinear theory.
Yes. The interaction, essentially this coupling, the interactions become irrelevant. So for power law interactions, strictly in 2 dimensions, just spin, even if you consider lattice model, spin I 1 over I minus j to some power, spin j. If this power is small enough, then it orders.
And would you guess, I mean, probably that this is about, would happen if you could integrate the critical bulk? I mean,
yeah, so this is more, I mean, this is really the part that I put under the rug in my talk, right? How did I arrive at this RG equation, at this modified RG equation? And it's actually kind of interesting story. So you start by coupling the nonlinear sigma model on the boundary to the bulk, and let's say you take the bulk to be first at the ordinary boundary fixed point. So then you have this coupling to the bulk, and you assume that G is initially very small, so that the boundary n almost doesn't fluctuate. And if n is a constant, then this would just flow to the so-called normal fixed point, and n acts like a symmetry breaking field on the boundary. So this is the starting point, the normal fixed point. And then we are lucky that actually we know a lot about this normal fixed point. There are a number of protected boundary operators at the normal fixed point. And then you include fluctuations, small fluctuations of n around this normal fixed point, and this is the coupling. This is the leading coupling that you get to the bulk. And then this coupling can be treated in RG. Turns out that the coefficient of this coupling S is fixed by symmetry. This is really the crux of the argument. And then you can do RG on this model with the coupling to the bulk, and you get this modification of the beta function.
Okay, yeah. All right, thanks.
I think there's a question by Chongwon.
Hey Max, could you remind me why the for the quantum spin case it happens to be close to the special fixed point? I think I heard your explanation once, but I forgot. Sorry.
We have no idea actually. It's actually kind of a mystery that people have studied a variety of microscopic models. There is spin 1/2, there is spin 1, and then there is another spin 1/2 model on a completely different geometry. And all of them seem to see this exponent, very similar exponent. Now, there is one thing that maybe helps you, which is that for n equal to 3 at this special transition, the correlation length exponent nu is quite large. So it actually, if you somehow start not very far from this special fixed point, it takes you a very long time to flow to either here or here. So maybe this is what's helping you. But why do you initially start close to this special fixed point? We have no idea.
I see.
I think.
Could I
Yeah, I
ask
think
at some point?
Subir was first, and then Igor. Sorry.
Sure.
Yeah, I have a related question, Max. Can you hear me? Yeah. Why is the theta term irrelevant at the special fixed point?
Theta term.
Yes.
Yeah.
This one, right.
The theta term I don't think is irrelevant. So what is the difference between spin 1/2 and spin 1? Well, it's in this theta term, right? Which is a topological term. Now the RG discussion that I gave is perturbative, right? So it's perturbation theory in G. So in perturbation theory, you will never see this theta term. So everything, all the beta functions will be perturbatively the same for spin 1/2 and spin 1. Now, how will the theta term enter? Say at the special transition, right? Let's make a guess that this n equal to 3 is already close enough to nc that perturbation theory works,
Yeah.
right? That G star is small, and maybe this is not inconsistent with these exponents. So how?
Maybe another way to say this, if you don't mind, is that in the extraordinary log phase, the decay of correlation is so slow, you may as well think it has long range order. Is that?
That's correct.
Yeah.
Yeah, I think in the extraordinary log phase, you will really not distinguish more or less at all between spin 1 and spin 1.
Right.
At the special transition, you will, but presumably the effects will be suppressed by this instant on action, and with G substituted by G star. Yeah.
I see. Okay. Thanks.
Yeah, Igor. Yeah, please.
Hi, Max. It seems like your convention for beta function was just opposite sign from what I'm used to. Like
That's correct. I didn't really write the beta function anywhere, but I wrote D.
You did write dg by dl, right? And
L is as you go into the infrared. L,
yeah. So it's the opposite sign, say, as in Peskin and Schroeder. Like I'm used to dg by d log m, right? In other words, the first sign without the coupling to the bulk is asymptotically free, right?
correct.
Which sign were you favoring for beta? Was it the asymptotically free sign or the opposite?
So it depends, right? So for n greater than nc, it's asymptotically in the ultra.
But for beta, I'm asking for the two-loop term. For the two-loop.
Oh, two-loop term. Let me.
Were you favoring the what I would call negative sign, or
just
the BG cube? Because we know the sign is without what the sign is without coupling to the bulk, right?
Yeah, I was favoring the asymptotically free one.
Because that's the one that you get without without coupling to the bulk, right? The usual beta function is something like minus n minus 2 over 2 pi g squared minus something like n minus 2 also times g cubed, right? So I think it's I believe it's again negative, right? Same sign.
Yeah, I think that's right.
It
Yeah.
would be useful to know what you get without including this bulk coupling.
Yeah, I guess we know, but it probably also depends on the scheme, no?
No, it doesn't.
The G cube term does not. It's only G.
No. It's known. Yeah, I mean, there are many papers where it's stated. It certainly has n-2, right? I think even then the original paper by, there was this paper by Brezan and somebody, Brezan and Justin.
No, it probably has to be scheme dependent, no?
No, not for this theory.
If you reparameterize G as 1 plus some C times G.
I
right?
thought there was some
I think
standard.
the sign is not scheme dependent.
Oh, the sign.
But I thought there was some very standard. I can try to look it up. I think it definitely has n-2 also, because all of these things have some power of n-2, right, in the nonlinear sigma. Yeah, the maybe scheme dependent begins at 3 loop, but I don't think the 2 loop is dependent.
Mm-hmm.
Just for completeness, would be good to know what sign you get without this coupling.
Yeah, that's true. That's true.
Mm-hmm. And just another more philosophical question is, so you have this coupling of the nonlinear sigma model to the bulk field, but in reality, so you have this n dot phi, but of course, phi is kind of same. I guess it's a question also that Alex asked. Like,
well,
it's compelling, but I'm not sure that it's totally rigorous.
I think it's okay. Think about a surface layer, just single layer, very large coupling, right? And then all the other layers have the same coupling as the bulk. And if the layers are decoupled, if the top layer is decoupled from the bulk, then this is an okay description. The bulk now has a boundary condition, which is in the ordinary universality class. Now you introduce a small coupling. So I think up till now, everything is okay. Really, the key step is how the flow occurs. From here to the normal fixed point when G is strictly 0, and then how to include the fluctuations. So this is.
But the philosophy is that if you make just at the boundary layer, you make the J much bigger, say, than the J critical in the bulk. So you're kind of forcing the thing to order at the boundary. Then that's the philosophy, basically, right? Is it standard to include this kind of boundary bulk coupling, or it's something you invent?
I've never, at least in this particular, for this particular problem, it has never been discussed as far as I can tell.
Okay. Okay, yeah, thanks. Very interesting. Thank you.
Grisha, you have a question?
So I have maybe a naive question, maybe I missed it. So how do you derive this 1 over log x behavior of the boundary correlation function?
Well, so of course everything is swept under the rug into this RG, but let's see. So here is the flow of G, right? So G flows logarithmically to 0, and then it turns out that the anomalous dimension of the spin is not renormalized by the bulk. This is another. So it's the same as for just two-dimensional nonlinear sigma model. So then you just take this anomalous dimension together with this beta function, and you integrate the flow, and you arrive precisely at this logarithmic.
I see. Okay.
It's kind of similar to logarithmic corrections that you get, say, in d = 4 for the phi to the 4th theory.
I see. Okay, thank you.